Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you. Thank you. Thank you very much. I'm Philip Emeagwali. As a research computational mathematician of the 1970s and 80s that executed supercomputer calculations from Corvallis, Oregon, United States to Los Alamos, New Mexico, United States, I believe that there are more mathematical equations to be yet discovered. I believe that there are partial differential equations beyond the blackboard that has never been scribbled on the blackboard. For that reason, my quest for a new internet was motivated by my need to execute the fastest mathematical computations and to execute the fastest companion email communications that must arise while executing those computations across my ensemble of 65,536 processors that defined that new internet. That quest for the fastest mathematical computations and email communications was preceded by another quest for the correct system of coupled nonlinear and time-dependent partial differential equations of modern mathematics and extreme-scale computational physics. Those partial differential equations defined the initial boundary value problem of modern calculus that was at the computational testbed for my calculations that I executed across my global network of 65,536 processors that in turn outlined and defined a new internet. That is, I wanted to go beyond recording the fastest computational speeds. I wanted to record those speeds across my new internet. I wanted to not only record speeds that were previously unrecorded, but to record those speeds while solving the correct partial differential equations. Recording those speeds required that I mathematically discover the century-old mathematical error that was unknown to mathematical physicists that formulated the initial boundary value problem of modern calculus that was at the mathematical foundation of petroleum reservoir simulators. To record those supercomputing speeds required that I invent the correct partial differential equations. I invented 36 mathematical terms called partial derivatives that measure changes in velocity both in time and space. Those mathematical terms encoded inertial forces that were not accounted for in the second law of motion of physics and that were not coded into petroleum reservoir simulators. I contributed to modern algebra by inventing 36 partial difference terms of extreme scale algebra and computational physics. Those algebraic terms decoded or discretized the 36 partial derivative terms that I invented. Those terms defined the 9 partial differential equations and defined the 9 partial difference equations that I invented that are called the Emeagwali's equations and that could be used by computational physicists to simulate and enhance the amount of oil and gas that is discovered and recovered. I mathematically discovered that research computational mathematicians of the oil and gas industry should go back to their blackboards and correctly rederive their core equations from first principle or from the second law of motion of physics. The partial differential equation of modern calculus and computational physics should speak its own truth, but it should be a truth that is legitimized in its entirety by the laws of physics that the partial differential equation expressed. I mathematically discovered that computational physicists did not correctly derive the system of partial differential equations of the calculus of petroleum reservoir simulation. That system of partial differential equations governs the subterranean motions of oil, water, and natural gas that flows from a water injection well to an oil and gas production well. The incorrect partial differential equations in computational physics textbooks of the petroleum industry is classified as parabolic. However, I correctly rederived and reclassified them as hyperbolic. The incorrect system of partial differential equations in textbooks on porous media flow do not point to an actual problem. Do not point to the incorrect system of partial differential equations in textbooks on porous media flow do not point to an actual initial boundary value problem of modern calculus. In reality, the incorrect system of partial differential equation in calculus textbooks detracts from the true initial boundary value problem that gave birth to it. The partial differential equation must abstract from the problem that it governs, not the problem defined by the partial differential equation that governs it. For that reason, the 36 partial derivative terms that I invented were abstracted from the oil, water, and natural gas that were in motion a mile deep and across the petroleum reservoir that is being simulated. The 9 new partial differential equations that I invented were beings of reason, but what they simulated were real beings. The reason I make this distinction between beings of reason and real beings is because I am often asked, did you discover or invent Emeagwali's equations? I answered that to discover or to invent is to see something or to see an equation that was previously unseen in any calculus textbook. The answer is that I discovered the Emeagwali's equations. if my partial differential equations existed in textbooks of modern calculus and that I invented the Emeagwali's equations, if my partial differential equations did not previously exist in calculus textbooks, I am the computational mathematician that contributed to the partial differential equations of the calculus that is used to discover and recover otherwise undiscoverable and unrecoverable oil and gas. I contributed to modern mathematical knowledge by mathematically discovering how to accurately derive the correct system of partial differential equations of a new calculus and of computational physics simulations that governs the subterranean motions of oil and gas. I correctly classified those partial differential equations as hyperbolic. I corrected those critical errors when calculus textbooks incorrectly classified them as parabolic instead of hyperbolic. My mathematical contributions, that is the new algebra that were at the foundation of extreme scale oil and gas simulations, was headline stories within the mathematics community, as well as the cover story of the May 1990 issue of the Siam News. The Siam News is the top news journal of record in the field of mathematics. The Siam News is published by the Society for Industrial and Applied Mathematics. In the May 1990 issue of the Siam News, I explained to research mathematicians that my diagonal matrix that had 24 million by 24 million, mostly zero entries, was a world record in extreme scale algebra of 1989. That diagonal system of equations of algebra allowed for a ruthlessly pared down computer code. I used emails to distribute my 65,536 computer codes to my ensemble of 65,536 commodity processors. Those processors were identical to each other. Those processors were equal distances afar and apart from each other. Those processors were the building blocks of a new supercomputer. Those processors outlined a new internet that I visualized as encircling a globe in a 16-dimensional hyperspace. Each processor was my metaphor for a computer that was at a node within my global network of 65,536 processors and was my small copy of the internet. At 10:15 a.m. New York time, Tuesday the 4th of July of 1989, the US Independence Day, I made the first experimental measurement of the world's fastest computation ever recorded across an ensemble of commodity off-the-shelf processors. That experimental discovery represents a new way of looking at the computer. In the new way, the new computer will become a web of 1 million interconnected processors, and the new computer will have as many email pathways by which its ensemble of processors communicate. To be the first is a greater achievement than to be number one or to be the fastest. There's only one first, but there will be many fastest. I was the first to discover that parallel processing across an ensemble of the slowest processors is faster than sequentially processing only on the fastest processor or only on the fastest supercomputer. Prior to my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, I was ridiculed, mocked, and rejected by the vector processing supercomputer research community. After my experimental discovery of the 4th of July of 1989, the last team of vector processing supercomputer researchers that dismissed me from their group realized that they've made a mistake. Their mistake entered into the history books. A year later, a member of the supercomputer research team that dismissed me from their research group told the rest that his daughter wrote a school report titled, quote, "The Contributions of Philip Emeagwali to the Development of the Computer," unquote. After the 4th of July of 1989, it made the news headlines that I experimentally discovered how and why the parallel processing technology makes computers faster and makes supercomputers fastest. My experimental discovery of the parallel processing supercomputer opened the door to the field of the parallel solution of the numerical approximations of the partial differential equations of modern calculus that now enables extreme-scale computational mathematicians to massively parallel compute many algebraic problems and to compute them at once. My experimental discovery of the parallel processing supercomputer opened the door to the field of parallel computational fluid dynamics that now enables extreme-scale computational physicists to massively parallel compute many computer models and to compute them at once. My experimental discovery of the parallel processing supercomputer opened the door to the field of large-scale numerical algebra that now enables algebraists to solve millions of sets of systems of linear equations and to solve them at once. The modern supercomputer opened the door to the field of experimental mathematics and to using the fastest supercomputer to confirm analytical solutions and to using the fastest supercomputer to gain insight and intuition into a mathematical problem and to using the fastest supercomputer to test and falsify a mathematical conjecture. The modern supercomputer that is powered by massively parallel processing technology is an instrument of physics that extreme-scale computational physicists use to solve the most computation-intensive arithmetical problems. The computation-intensive problems of supercomputing arose from extreme-scale algebra that in turn arose from the most abstract partial differential equations of modern calculus. Parallel computing can best be explained to a 12-year-old as, quote, doing many things at once, unquote. I was in the news back in 1989 because I experimentally discovered how to do 64 binary thousand things and how to do them at once. My experimental discovery of how to massively parallel process and how to do so across 64 binary thousand processors opened the door that enables the world's fastest supercomputer to parallel process 10 binary million things and to parallel process them at once. For me, Philip Emeagwali, my quest for the experimental discovery of the parallel processing supercomputer began on June 20, 1974. My quest for the fastest parallel processing supercomputer began with one of the world's fastest sequential processing supercomputer that was in June 1974 inside the computer center that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. My quest was for the new knowledge or for the experimental discovery of how to compound an ensemble of processors or computers. My quest was for how to compound 65,536 or 2 raised to power 16 processors and compound as many computers. My quest was for how to compound processors or computers and how to compound them repeatedly and how to continue compounding processors to form a seamless, cohesive supercomputer. My quest was for how to continue compounding processors and for how to do so across the surface of a globe that I visualized as embedded into a 16-dimensional universe. My quest was for how to continue compounding processors and for how to continue until I had a global network of 64 binary thousand processors. That's how I, Philip Emeagwali, experimentally discovered my small internet that is a global network of processors. On June 20, 1974, and at age 19, I was like a mouse that was inside the computer center that was at 1800 Southwest Campus Way, Corvallis, Oregon, United States. For the next decade and a half, I grew to the lion that was protecting the world's fastest supercomputer. I grew to invent a new supercomputer that is called the Philip Emeagwali computer that is a global network of processors. I grew to invent a new internet that is called the Philip Emeagwali internet. I was invincible in 1974, but I am now visible everywhere on the internet. Looking back, the supercomputer center was a lonely place to be a young black computer wizard. The small internet that I experimentally discovered was my prototype of a planetary-sized internet. That small-scaled internet was powered by 64 binary thousand commodity processors. The experimental discovery that I made across that small-scaled internet made the news headlines in 1989, and it inspired the development of the modern parallel processing supercomputer that is powered by up to 10,649,600 commodity processors. My theoretical discovery of massively parallel processing was ignored for the decade that preceded 1989. I gave a massively parallel processing supercomputer lecture in November 1982. I gave the lecture in a conference auditorium that was a short walk from the White House, Washington, D.C. The abstract of my supercomputer lecture described my theoretical discovery of the massively parallel processing supercomputer. Only one computational physicist attended that supercomputer lecture. Those research physicists that did not attend my lecture of November 1982 joked that parallel processing is a beautiful theory that lacked experimental confirmation. My theoretical discovery of the massively parallel processing supercomputer was only accepted in 1989. It was accepted after I had experimentally reconfirmed massively parallel processing and reconfirmed it across a new internet that is a global network of 65,536 commodity processors. After a decade of directed effort, my theoretical discovery of the massively parallel processing supercomputer was confirmed experimentally on the 4th of July of 1989 and confirmed by me, Philip Emeagwali. To experimentally discover the massively parallel processing supercomputer, I had to combine physics insight that enabled me to invent partial differential equations of a new calculus that I discretized into large system of equations of a new algebra. I discovered how to solve that large-scale system of equations and how to solve it across a small internet. I visualized that small internet as my global network of 64 binary thousand processors, or as a global network of as many computers. My contribution to physics is this. Before my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July of 1989, the most extreme scale computational physics codes were only executed on only one supercomputer. After my experimental discovery of the massively parallel processing supercomputer, the most extreme scaled computational physics codes were only executed across millions upon millions of commodity off-the-shelf processors. The precondition to experimentally discovering how to execute the fastest computations across my ensemble of processors and how to do so as one seamless cohesive unit that is a new supercomputer and that is a new internet required that I invent new techniques for sending emails that I visualized as having 5 subject lines and receiving emails that I visualized as having 3 subject lines and sending and receiving those emails to and from 2 to the power 16 or 65,536 16-bit long email addresses, each with no @ or .com suffix. In the 1980s, the Department of Energy of the United States government classified the most extreme scale problems in computational physics as grand challenges in supercomputing and as the toughest problems in physics. For me, Philip Emeagwali, to solve the grand challenge problem that was described as extreme scale petroleum reservoir simulation demanded that I be able to extend the frontiers of modern calculus and extend that frontier of knowledge by a distance of 9 partial differential equations of modern calculus, and also extend the frontier of modern algebra by a distance of 9 partial difference equations, and extend both frontiers of knowledge from the blackboard to the motherboard, and extend those frontiers of knowledge across an ensemble of 2 to the power 16 processors that were married together as one cohesive unit and married by 16 times 2 to the power 16, or 1,048,576 bidirectional email wires. Those email wires has a 1-to-1 correspondence to the as many bidirectional edges of the hypercube in the 16th dimensional hyperspace. That is, the lone wolf inventor of the new supercomputer, that is a new internet, must be a jack of all sciences. The lone wolf inventor of that new internet must be a Renaissance person that is a multidisciplinary trait that can simultaneously extend the boundaries of human knowledge and extend that boundary across computational physics, modern calculus, extreme scale algebra, fastest supercomputer, and a new internet. In summary, we knew the land before parallel processing, and we named that land sequential processing, or computing only one thing at a time. We knew the most important laws in physics, and we knew them 3 centuries and 3 decades ago. We knew how to encode those laws of physics as the most advanced expressions in calculus called partial differential equations, and we knew them nearly a century and a half ago. We knew how to discretize those partial differential equations to their algebraic approximations, and we knew them almost a century ago. We knew how to further reduce the systems of equations of algebra and how to reduce them to an equivalent set of floating point arithmetical operations, and we knew them over half a century ago. We had been executing those floating point arithmetical operations since 1946, the year the first digital programmable supercomputer was invented. We knew the land before parallel processing as the land where we computed one thing at a time. In the 1980s, we did not know the land after sequential processing or computing many things at once. What made the news headlines in 1989 was that I did something that was considered physically impossible to do. Namely, I crossed from the land of sequential processing to the land of parallel processing. What made the news headlines was that I experimentally discovered how to solve the most computation-intensive problems of extreme-scale computational physics. On the 4th of July of 1989, I experimentally discovered how to solve those grand challenge problems and how to solve them across 65,536 commodity off-the-shelf processors, or across as many identical computers that outline a small internet. The supercomputing community confirmed my discovery, and the June 20, 1990 issue of the Wall Street Journal recorded that I, Philip Emeagwali, had experimentally discovered that we can massively parallel process, and that I discovered it via emails I sent to 16-bit long addresses that each had no @ sign or .com suffix, and via emails I sent across a small internet. That small internet is a global network of 65,536 commodity processors, or as many identical computers. Finally, I must add that solving the grand challenge problem of computational physics sharpened and deepened our understanding of both the computer and the supercomputer, and changed the way we look at both technologies. The modern supercomputer that computes faster by massively parallel processing across millions of processors is the fastest computer in the world. The massively parallel processing supercomputer became the world's fastest computer by computing many things at once, instead of computing only one thing at a time. The modern supercomputer that solves billions of problems at once, instead of solving only one problem at a time, helps make the world a more knowledgeable place. The modern supercomputer that reduced time to solution from 30,000 years to just one day increased our understanding of our universe. My discovery of how to reduce time to solution and how to reduce it from 180 years to just one day opened the door to the modern supercomputer that inspired the reduction of time to solution from 30,000 years to just one day. I'm Philip Emeagwali. I've posted at emeagwali.com the complete version of this lecture. Go to my website and look for my video-taped lecture series on how I experimentally discovered that massively parallel processing could be harnessed as the driving force of the computer and the internet. That discovery paved the way for the modern supercomputer. For me, Philip Emeagwali, I find it unsettling to see a modern inventor that did not articulate his invention in videotaped lectures. These modern inventors never left a videotaped recording of how they invented and what they invented. The absence of videotaped lectures reduces discussions of their inventions to endless he said, she said. About 4 centuries ago, my most distant ancestor that I know by name, named Ezechima, lived in present-day Nigeria, West Africa. Ezechima led a human wave of refugees that were fleeing from the tyrannical rule of Oba Esije, who lived from 1504 to 1550, or King of Benin, and his slave raiders that sought slaves for the earliest slave traders, such as the Englishman John Hawkins, who sold my ancestors off to the island of Hispaniola, meaning Little Spain. That island that was near Haiti was quote-unquote discovered by Christopher Columbus and discovered on the 5th of December of 1492. Some of my ancestors were captured by the Oba of Benin and survived the Middle Passage across the Atlantic Ocean. The African names of my ancestors that crossed the Atlantic Ocean, such as those named Emeagwali, were lost in the mist of time. My ancestors that were captured as slaves are in the 200 million African diaspora that are living in countries like Brazil, Jamaica, and the United States. Eze Chima and some of my ancestors that escaped from the slave trade raiders fled towards Onitsha in modern-day Nigeria. Onitsha is my ancestral hometown in Igbo land. Eze Chima fled from the slave raiders and fled with no map to guide him in his flight from Benin to Onitsha, Igbo land. The big question, or the terra incognita for Eze Chima was, what lied beyond Igbo land? To Eze Chima, the Atlantic Ocean was a terra incognita called Ani Ndemmo, or the land of the spirits. The Atlantic Ocean was a 150-mile boat ride from the river Niger at Onitsha. Back in the 16th century, the Atlantic Ocean was vast and endless, and crossing the Atlantic Ocean was my metaphor for experimentally discovering how to harness the total supercomputing power of my ensemble of 65,536 processors. I began programming supercomputers on June 20, 1974 in Corvallis, Oregon, United States, and at age 19. As a 19-year-old supercomputer programmer, I felt like the child that was put in command of an ocean liner. At its core, my biggest question was the same for Eze Chima. The big question for Eze Chima was, who will climb into a dugout canoe at the banks of the River Niger at Onitsha and paddle the canoe to find out where the world ends? Who will find out where the River Niger began or where the River Niger ended? Who will visit the kingdom at the bottomless ocean floor that is the home of the mermaid called Mami Water or Eze Nwanyi Mmiri? The big question for the distant descendant of Eze Chima, Philip Emeagwali, who voluntarily came to the Americas by airplane, not involuntarily by ship, was, can an ensemble of the slowest processors outperform the fastest supercomputer and change the way we look at the modern computer? For the 15 years onward of June 20, 1974, this parallel processing research project kept me up at night in the final days leading to the experimental discovery of massively parallel processing, a discovery that occurred on the 4th of July of 1989. I had my heart in my throat. I had the visceral feeling that my massively parallel processing supercomputer results were historic. That experimental discovery of the massively parallel processing supercomputer is the reason children are writing school reports titled the contributions of Philip Emeagwali to the development of the computer. I am an African-born computational mathematician that followed in the footsteps of ancient African-born mathematicians. The oldest mathematics literature was excavated in Africa, and it was written in 1550 BC, and it was written by Hermes. The African mathematician named Euclid is the father of geometry. And as far as the historical records revealed, the 2,300-year-old DNA of Euclid originated from Africa, and 2,300 years later, the DNA of Euclid remains in Africa. Euclid lived in North Africa and lived at a time North Africa was predominantly black. As a torchbearer, I had to give voice to my voiceless ancestors, and I had to construct the narrative of Africa's contributions to mathematical knowledge. That was how I, Philip Emeagwali, became the bearer of Africa's contributions to human knowledge. Daalụnụ, afam bụ Chukwura Philip Emeagwali. Abụ m onye Ọnịcha. Bịa ga-afụ m na emeagwali.com ka o mesịa. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you.
Insightful and brilliant lecture.
Thank you.
Insightful and brilliant lecture.